No, that is non-negative, right? If it's irreducible, then the arithmetic genus of L is 0. In particular, it implies that the curve is smooth. Now, if I have a value here, I can write I star k plus the bar is k. Okay. Let me put k bar is simply the canonical divisor of x bar. K and k is the canonical divisor of x. K plus the proper transform of the bar, and you have some coefficients here where EI are irreducible components of the divisor contracted by E. So there's an exceptional locus of pi. It's a divisor. It has some components. I put all of them here, and there are some numbers here. So clearly, this morphism is not doing anything over points which are smooth because it's a minimal resolution. So the only difference comes from resolving singularities. And this is why this is almost the same, but there's some difference over the singular locus, which is expressed in terms of some coefficients and some near the components contracted by this morphism.
Sorry, I missed what is E X? Oh, that's exceptional.
Yes, that's the exceptional locus. In this case, it's a divisor. Okay, so picture, you have a singularity here, and you have some you have the exceptional locus here. Okay, now these CIs are rather important here. So this is called the coefficient, this is the notation of EI over X bar D bar. And it's called the coefficient. Now, really, EI, which is somewhere here, E1, E2, E4, E something. These things do not live on X bar, they live on X. Their image on X, the so-called center, is a point here. Still, it's analogously to, like here, the divisor D lives on a surface, so that would be its coefficient. But this generalizes to this divisor living on some resolution over X bar. Now, the question is, well, this number depends on the resolution. And an exercise for you.
I'm sorry, I'm confused here.
Yes.
Pi that goes from X, which could be singular, to X bar, which is smooth. No,
it's a resolution, so X is smooth.
Okay. Oh, now okay. And X bar is.
And X bar
It's not the same X as no.
No, it's not.
Oh, you change your notations. Huh?
Yes, I changed the notation slightly.
It was going in the wrong direction. Okay, perfect.
P
Singular. Okay. So it's you have a reverb.
No, it's okay.
No,
try to keep bars for single.
You blow up in order to
yes,
the resolution smooth, to have a smooth.
Okay. It's known that such a thing exists.
Just for everybody here, it's a theorem that in this case just a sequence of blow-ups.
I mean, it depends what do you call blow-ups. It's not a blow-up of a smooth point.
No, sure. Blow-up of this singular.
Yes, in a sense, that's true. But to say that you can blow it one by one to get irreducible curves, that's something else. I didn't say that it's true, but it's true that you can do it. I won't use that fund. What's the second term in the problem? The second term? Okay, that's the proper transform of the bar. So actually, the notation for the proper transform is it's the pi minus 1. It's inverse morphism, which is a birational map. It induces something on divisors. So this thing is the proper transform of the bar, and that's the usual notation. Okay, so there are some numbers here, and an exercise for you. CI does not depend on the choice of a resolution. Here I used a minimal resolution, so it's obvious that this way it's not. It does not depend on the resolution because minimal resolution in case of surfaces is unique. But actually, you can compute it using any resolution. If C, so yeah, C does not depend on the choice of a resolution.
Just recall what do you mean by minimal?
Minimal in the sense of domination. So if X bar is singular, then pi is a resolution, and you have natural relation of resolutions if there exists eta such that
it could be factorized.
you have such a factorization, then and eta is not an isomorphism. Then this resolution non-trivially dominates this one, so this is not minimal. Okay, it's minimal in the sense of the existence of such derivative. Is it clear?
Could eta be a covering, smooth covering?
No, this is just it's a morphism of resolutions.
Yeah, sure.
Resolutions are birational morphisms, right? So will exist.
I would say that not the identity and neither covering.
Birational proper morphism, which is not an isomorphism. Okay. In a sense, it's the same as you cannot load down anything here without destroying smoothness. Good. So we have the coefficients, and now what? Okay. Now I wanted to discuss something you mentioned. Like, let's try to understand what happens exactly with this generalization if D is non-zero. What happens if D is non-zero? So let's assume that D is reduced. So all coefficients are equal to 1. And still X is smooth. So this condition L squared negative and L times K plus D negative this part can be, there are two cases. Case one, if L is not inside D, then clearly LD is a non-negative number because D is an effective divisor. It does not contain L. So this is just the number of times L intersects D. It's non-negative. So in particular, you get that L squared, LK is negative, right? But you already know that L squared is negative. So again, it's a -1 curve. We already discussed that. And in fact, a -1 curve which does not meet D, because if you remember, a -1 curve meets the canonical divisor the negatively, the intersection is -1. So in fact, you also get that L times D is smaller than 1. So LD is 0. So L does not meet D, right? Okay. Now the problem, so that's perfectly fine. It's not only smooth, but also there are some bounds on here. They are pretty naive, but there are some bounds, and there will be some bounds in general. If the curve is not in D, then actually I did not use the fact that X is smooth here. The same goes through. If L is not in D, then the intersection with D is non-negative, then the intersection with K is negative. So you get this condition plus some additional bounds on the intersection with D. And that's how it works in general. The problem comes from this case, where L is a component of D. And now you can write this condition. So we know that this is negative. So I'll write it as D minus L plus L times K plus L. So D is reduced and L is a component of D. So if I subtract D, then L is not anymore in D minus L. So again, this is a non-negative number. In fact, it's a definition of a branching number of the component L in D. branching number of L in D for obvious reasons, because it's the number of times L meets the remaining fragments of D in the sense of intersection theory. Okay. Now this guy here. Okay, so far I don't know what's the arithmetic genus, so let's just use the adjunction formula as written there. So it's 2 times the genus of L minus 1, and this is supposed to be 0. So it's what? So it's bigger or equal to than 2 times the yeah, the arithmetic genus. Okay, let's imply that the arithmetic genus of L, which is always non-negative, again has to be 0. Right, because if it's at least 1, then it's non-negative, and it is supposed to be smaller than 0. So that's nice, and then what? Then we have minus 2 here, so we can rewrite the condition as beta of L is smaller than 2, so it's smaller or equal than 1. Okay. Now, such a thing is called a rational.
Are you assuming that D has integral coefficients here?
Yes, D is reduced. So all the coefficients are equal to 1.
But so like over there it was in the rationals, but usually
There is general. Now we are considering the simple, one of the simplest cases.
thank you.
Okay, so in this case, already in a very simple case where X is as good as possible and D is reduced, could be even simple normal crossing as you wish. It cannot be better. You do not get a condition, so actually, and this is equivalent. If you have this thing, and you should of course keep independently this condition L squared smaller than 0. So I call this a rational type of D for obvious reasons, because it just says that there's some divisor D minus L here, and it meets L transversely in 1 point, and it looks like that. So and L squared is negative. But this does not say anything about the self-intersection of L other than it's negative, right? You do not anymore have the condition that L squared is minus 1. And indeed, if you can, if you take an example, a simple example, so let Fn be a Hirsebruch surface. So it's the utilization of the O plus O of n. Let's say n is positive. So there exists a curve here, a section. So this has a P1 vibration onto P1. And there exists a section such that its square is minus n. This is well known. And now consider the log surface Fn with this section. Smooth projective surface, smooth irreducible curve, P1, with negative self-intersection. When you do the computation, C square is, it's by definition minus n is negative because n is positive, and C times KFN plus C by adjunction is 2 times the arithmetic genus of C minus 1, so it's minus 2, definitely negative, and that's it. So this condition holds. Now, the problem, which we will see in a minute, is that I want to use this definition of a log exceptional curve to proceed with a sequence of contractions, which is called the minimal model program in this case. And you already see the problem that smoothness is not any more respective. So I want to say that given a log surface XD, a sequence of contractions. Okay, let's say that this is X1, D1, this is my XD. A sequence of contractions. Usually I would call it X bar, D bar, such that sigma I of sigma I star of di is di plus 1, and Li, which is the exceptional component of sigma I, is log exceptional on xi di. This is called the minimal model program. Run the program.
Sorry, di plus 1, what do you mean by 1 here?
No.
Ah,
Sorry.
So minimal model run, you said?
Yes, because it's a specific choice of a sequence of contractions. So minimal model program is a general theory.
Right.
This particular choice, and there might be many ways to choose log exceptional curves. Nobody said it's unique.
Mhm.
Each such a choice is called minimal model program run. Maybe like that, the run of a minimal model program.
Right.
Now, this is actually a partial run, because so far I did not say that it cannot be extended. But let's make it so that X bar D bar has no log exceptional curve.
so X1 is smooth here.
No. X is in general Q factorial. But in such generality, I need to say that this property is respected. Actually, there are several points I need to make, but let me finish the definition. So X bar, V bar has no log exceptional curves, and this by definition means it's minimal. It's a minimal model. It's a minimal log surface. Comma, a minimal model of the initial log surface XD. Now, there are several points here which I should explain. So first of all, there are theorems which need to be used here. So first of all, you should know that if X is as here, X is Q factorial and D is a boundary. So remember, there are some conditions on the coefficients. They are between 0 and 1. In our case, they are rational numbers.
So we start by
So I want to say that if L is log exceptional on XD, then there exists a contraction, there exists a birational morphism, which I will denote by a CTR with index L, which goes from X to, in this case, it will be X2, but in general, let's say X prime, such that a birational morphism and X prime is normal projective, such that the exceptional locus is exactly L. So this is a baby version of the contraction theorem. Such a contraction exists, okay? So once I have such a curve, the contraction exists. And now I also need to argue, but I won't do this here. Now you need to argue that X prime is Q factorial if X is. And now this makes sense. So I start with something Q factorial. I'm looking for a log exceptional curve. Remember, this was L squared negative and L times K plus D negative. If I can find such a curve, then the theorem tells me there exists a contraction. The image is still Q factorial. I just push, make a direct image of the boundary, so the coefficients are the same. Maybe some of the components of D disappear, because it could be that L is a component of D, so then it's contracted. The image is a normal surface, which is Q factorial, and I can repeat my query. If there is another curve, I proceed, and at some point I get to a log surface so that there is no more such a curve. Why is it a finite process?
Using rank of homology every time.
Exactly. This process is finite. You can, for surfaces, it's easy. You can define the rank of X as the rank of the Néron-Severi group of X. Let's say tensor over Z with Q, the dimension of the Néron-Severi group, and you know that this has finite dimension. This is called the Picard rank of X, and it's finite. So each time I contract a curve, the Picard rank decreases, so the process is finite. Okay.
I have a question. The theorem works just for surface, I think.
Yeah.
Because,
It's only
canonical or Coyote, things like that.
For surfaces, it works in particular for the class of Q factorial surfaces. In fact,
But in general, you need Coyote or log canonical in higher dimension.
yes, in general, you need some additional assumptions. That's true. But the theorem is for surfaces.
Yeah, I had just a qualitative question exactly about this.
Mm-hmm.
Where do you use the fact that it is a surface? So you have the because you have a curve meeting a co-dimensional divisor, so you have
I think the fact that this is a number.
Oh, sure.
That's already the first thing.
Sure.
But there are several subtle issues here which I don't know.
But is it true in high dimensions? Because you could replace this part.
Yes, but you
I'm not
need to it correctly. That's true. Yes, and usually you need to add stronger assumptions on XD. Of course, you can define the coefficients the same way. That's perfectly fine. But then the question is, it's not. First of all, the contraction of L. You don't contract log exceptional curves. You study the Nef-Con in the space of cycles, one-dimensional cycles modulo numerical equivalence. You need to describe the structure of the cone on the side where K on the side where it's negative with respect to Kx plus D. You prove that it's locally polyhedral. Then you study extremal rays. To such rays, you have the associated contraction motions, but the contraction motion usually does not give you an image which is Q factorial. If it's not Q factorial, then you need to do something else, which is called the flip. Then you have the question whether flips terminate, whether flips exist, and so on and so on.
Okay, okay. So then does such a similar theorem exist in high dimension?
Yes.
It does exist.
It does, yes. You see here, first of all, what is very exceptional here is that this sequence is a morphism. In general, what you do is such a contraction can be a higher codimension surgery. And this usually that's actually the problem. If it's a contraction of a subvariety of codimension at least 2, then this is not anymore Q factorial. So then it's a big problem because you need to intersect. You at least want to do that, right? This makes sense in any dimension. It's a divisor and it's a curve, right? That's something to be replaced. And if it's not Q factorial, you need to make some surgery. You prove the existence of such a surgery which slightly improves X prime, but then this is not anymore a map, it's a birational map and so on. So forgive me, I'm not discussing that. Yeah, but the questions you should maybe check in Wikipedia is the existence of flips, determination of flips. That's actually, these are actually huge work, huge problems. And are huge problems.
To interrupt too much, but could you now that we have the definitions, could we just state in a few, just in a 1 or 2 sentences, what is the goal? I mean, which is a master? Yeah, what is what you're aiming for?
Yes, you see, so in the general naive goal would be to classify all varieties, in some sense. To do that, you are trying to make them smaller, like with surfaces. If you want to study smooth surfaces, it's a good idea to make them smaller and to understand the small ones, right? And how do you achieve that? For smooth surface, you prove that there exists a sequence of contractions of -1 curves, and then you characterize the final models. I mean, it's a partial characterization. If you're on the positive side, one option is that if the codaric dimension of the surface is non-negative, then the theorem says that you end up with a canonical divisor being numerically effective. Its intersection with every curve is positive. In particular, it's impossible to find a curve which meets it negative. But then there is this more interesting side when the codaric dimension of K is negative. And you most likely know that there are 2 options. The minimal model either has a P1 fibration, it's a P1 bundle over some curve, Sen theorem, or it's P2. Okay. In fact, we'll see analogs of this result here in a minute. So the answer is that if you want to study a variety, you want to make it smaller. Hopefully, the small varieties are more homogeneous. In a sense, you can say more about them. And then you hope that if you have some particular problem for your variety XD, then if you do understand the whole process and you have some strong structural theorems, then you hope to pull them back. But of course, the world of varieties is a complicated world. So it's a pretty naive thing. And on one hand, it's very strong, but that's true that I would say that we are at the level of, in many cases, we are at the level of existential theorems. There exists a sequence of contraction, it terminates, and so on and so on. To solve some very explicit, very, very particular problems, there is much more work to be done. Actually, you need to track back the whole process. I'll discuss this.
You try to find a minimal model within the birational class.
Yes, that's true. Yeah. So, okay. Now, so what are the good properties of this minimal model program run? So maybe let's state it as a theorem. So if psi it's a composition of these morphisms. If psi is an MMP run, and it maps XD onto a minimal log surface. then what should you know? Okay. So as you remember, given any surface, let's not. I don't want to confuse it with xd or x bar d bar. So if x is and e is any log surface, you have this notion of a divisor which lies over x. So you have some resolution, and there is a surface here. Y, there is you can take the total reduced transform if you wish. Anyway, there is some there might be some curve E here, such that I star of E is a point. So it's a curve contracted by E. And you have this notion of a coefficient of E over the log surface Y D. Let me recall that. You just write that pi star of ky plus D is ky tilde plus the proper transform of D plus, and there are some coefficients, and there is this coefficient C near your favorite component E, and that is the coefficient of E with respect to YD. Okay, there was this notion of a coefficient. It's just a coefficient in the pullback of the log canonical device. Okay, and it does not depend on the resolution as we already discussed. So now you have two surfaces. So you can imagine that you can have a divisor lying over D, and then it also lies over X bar by composition. So what you can prove, and it's actually easy, if E is a divisor over X, so it's like here, a divisor over Y could be a divisor on Y, or could be exceptional over Y. It appears on some resolution. Then the coefficient with respect to xd is x, let's say x bar d bar is smaller or equal than the coefficient of E x xd. So some of you might be familiar with the log discrepancy of E, and here is just 1 minus the coefficient. I prefer to work with that. So in a sense, when you run the MMP, there's one nice thing. If you measure the depth of singularities in terms of coefficients, these guys improve. Two, the Kodaira dimension of K plus D is the same as K bar D bar. 3, and that's something which you that was the goal in a sense, to have some structured theorems for minimal models. So okay, this is already assumed that it's minimal. So there are two options for X bar. Option 1, 3A, K bar plus D bar is exactly as it was in the case of smooth surface, is NEF, which means numerically effective. That is K bar plus D bar times any curve is non-negative. This is exactly how it was for projective surfaces. 3B, In fact, there are two subcases, but let me first state it as one, as it's usually done. There exists a structure of a Mori log Mori fiber space on X bar bar. And now I need to explain what does it mean. So what is this object? So log Mori fiber space on X bar D bar. It's a vibration over some base B such that the dimension of B is smaller than the dimension of X. The relative Picard rank is 1. In particular, all fibers are numerically equivalent. And to 1. And there are some negativity properties here. So K plus D, actually, let me write minus K plus D, is F ample, which means that for every curve C, such that C is contracted by, for every C such that F star of C is 0, K plus D times C is negative. So minus K plus D is ample on curves contracted by F, okay? Now, as you see, there are two cases here because the dimension of X is 2. So either the dimension of B is 1 or 0, right? And there are two subcases. So let me now discuss these two subcases for surfaces. So
what type of vibration is F?
what?
Said F is some type of vibration?
Yeah, it's a vibration which satisfies these properties. Dimension,
Any vibration. It could be a
proper morphism.
Connected fibers.
Yeah, connected fibers. Okay. So let me quickly check what is this condition saying for if so 3B case dimension of B equals 1. What does it say? So you have a surface X here, which might be singular. Sorry, X bar. Yeah, it's all for bar. It's all for bar. Let me add bars here. Sorry. Case when the dimension of B is 1. So you have a curve here. And let F be a general fiber. So it's a normal surface, so you have only finitely many singularities. So I can assume that F does not pass through any of them. And what do I have here? So F times K plus and and f times d. Now, once I know it's a zero curve, I know that this is zero, this is actually -2. So f times d is smaller than minus f times k, which is equal to 2. Okay, so for instance, if d is a reduced boundary, then this says that there is only one horizontal component, f times d, right? So if d is reduced, this means that f times d is at most 1. So how does the boundary look like? Well, there could be one horizontal component, and there are some fibers. Okay. Okay. And the second case, 3b case, the dimension b is equal to 0. Well, this just says that it's a contraction to a point. A trivial thing, but of course, I should add here that the rank of x is equal to 2. This is the all points fibers are numerically equivalent. So this relative Picard rank equal to 1 implies that the rank of x is 2.
Sorry, which kind of singular fiber we can have in the first case?
What type of fibers you can have in the first case? Well, to be honest, for this theorem, I don't care. And in case of P1 fibration, to answer this question pretty completely, first of all, you can say that you know very well the degenerate fibers of P1 fibrations. It's easy to prove that if you have a smooth surface and a P1 fibration, then every degenerate fiber is a blow-up of a smooth zero curve. So in particular, it's a simple normal crossing divisor. Okay. All such fibers are pretty easy to understand. But if you assume something additional on the singularities of x, then clearly you will have some restrictions on fibers. So far, I only assume that x is q factorial, so I don't think I can say much more.
And there are upper bound of number of singular fiber?
No.
Because it's finite. There are just finite singular fiber.
That's true. It's a finite number.
How much you can have for this term?
Arbitrary many. You can quite easily produce a surface one fiber, then you can repeat that. So you take a zero curve, you blow it up to -2, -1, -2, right? You can do it in 2 blow-ups. And then you can construct these 2 curves and you get a singular fiber with 2 canonical singularities here. And you can produce many such fibers. You can put this in a fibration. And the numerical condition.
Sorry, in your picture there, just below FD is smaller than 1. The picture there, you have the fibers, and what is this section? It's this represent. It's not D. What?
Yeah, it's part of D.
It's part, but then I do not understand then, because then FD should be equal to 0 then. Sorry to 1. Sorry to 1.
Yeah, because it was 2. It's smaller than 2. It's smaller.
Okay, because then it's 1. Okay.
Right? Because as the adjunction says that f squared plus fk is -2 for a curve of arithmetic genus 0. F squared is 0, so fk is equal to -2. If it's -2, then fd is smaller than 2. So fd in this case is smaller or equal than 1. Okay. Good. And then you have a final case where what do we know from this condition? It just says that the Picard rank of x bar is equal to 1. So all curves are numerically dimensional. That minus k bar is ample. And that's it. And this is called a del Pezzo surface of rank 1. Okay, how much time do I have? Hmm?
11, so you have 25.
25 days, okay, good. So here's a problem. So this thing can be singular. When I say del Pezzo, I do not assume smoothness because otherwise it would be just a P2 exercise. So a problem, an important problem.
Negative kx plus d example?
D?
Yeah.
I don't assume anything about D. Sorry, yes, you're right. Here and yes, in fact, I had a stronger condition here. This is ample. But you're right, thank you. But D is an effective divisor, right? So, and there's only one numerical class. So it's numerically ample, so it's ample, the sum of two ample divisors given ample divisor, in particular, and minus k bar is ample. But you're right, it's a log del Pezzo surface in a sense, yes. Yes, in particular, it's a del Pezzo. So minus k bar is ample, but in fact, there is also a boundary D such that even this stronger condition holds that this is ample. Yeah, thank you. If there's no boundary, you simply get the usual del Pezzo surface. And that's not my problem. The problem is, let me put the problem here. So if I really want to proceed along this strategy I promised, that I want to solve some problem for some particular surface, and let's assume that I have this sequence of contraction. Let's even assume that I have some understanding of this sequence. Let's even assume that I arrived at the minimal model and I understand the minimal model. Then I can pull back, and that was my strategy. Then I can pull back this information and somehow try to, using this information, some inequalities, some numerical properties, good numerical properties of the minimal model, I might be able to say something more about my initial problem. But here's already where the strategy fails, at least in this part. The problem is that there is no classification of minimal models. I mean, sometimes it's enough to know that you arrived at a divisor which is anti-empty right here. But very often you want to understand some much more concrete problem. And for that strategy to work, you would like to know, so what are exactly all these objects? Like in the smooth case, you have this structure theorem, which tells you it's a projectivization of P2 bundle. It's a P1 fibration over a smooth curve, or it's P2. Here, already this question is much more difficult. There is no classification of log del Pezzo surfaces of rank 1, even if you assume that singularities are nice. Say,
Nice, say what? The noise that. Nice, that is what?
yeah, like
LT.
bounded conditions. So
What do you think?
Capomata log terminal, but yeah. Let me stop with that. This classification even assume that the singularities are not too difficult. Okay. And actually, this is something which I want to discuss. I mean, P1 fibrations are fine. I would say, of minimal models here, in particular, of the Pezzo surfaces. The Pezzos of rank 1. Okay. So actually there were several problems related to Del Pezzo surfaces of rank 1. One of them was to understand the fundamental group of the smooth locus. And it has been proved that this fundamental group is finite. And this required already quite a lot of work. There was also a question whether the smooth locus is covered by images of A1. This has been done by Keel and McKernan in, I think, 1999 in a rather big book. Still, there was no classification. Recently, there are some papers claiming that this approach by Keel and McKernan is extended. There are some difficulties in low characteristics because, well, as usual in low characteristic, there are problems with vanishing theorems, which are used to prove some theorems of MMP. And there's especially problem with characteristic 2 and 3. And what I wanted to do today is I wanted to discuss some new geometric method, which will tell us how to classify Del Pezzo surfaces of rank 1.
Can you remind me what rank 1 means again?
It's the Picard rank. There's only one numerical class on this surface, like for P2. Actually, we have a P. Rank 1 means equals to 1. Okay, so how to classify them? Of course, I can assume that my surface X bar, which is a Del Pezzo of rank 1, is not P2. There's nothing more I want to say about P2.
Why not?
I assume in this setup, P2 is completely understood.
Understood, right?
Depends on your question. Sure, there are some questions I will be discussing, but it's about curves on P2, not P2 itself.
Yes, no.
But as for X itself, I'm not that much interested in P2. I want to have the classification of underlying Del Pezzos, so P2 is perfectly well understood. It says that rho of X bar is 1 and minus K bar is sample. Okay, in particular, I have a minimal resolution, which is non-trivial. So it's not P2, the rank of X is at least 2. So X has a P1 vibration. Because, let me maybe write something more here. So let D be the exceptional divisor, reduced exceptional divisor of the resolution. So in fact, I know that the Kodaira dimension of Kx plus D, well, it's smaller equal than the Kodaira dimension of K bar, which is plus D bar, but D bar is 0 because there was no boundary here. The exceptional divisor is completely contracted. So it's the same as Kodaira dimension of K bar, and this is an anti-ample divisor, so this is negative. In particular, I see that the Kodaira dimension of K plus, and in fact, I could put even a rational coefficient here, it doesn't really matter, but let's now write it as follows. So the Kodaira dimension of K plus D is negative. Okay. Right. So naively, you might think that, well, if for the log surfaces things work like projective surfaces, there should be an analog of the Sen theorem, right? Sen theorem tells you that if there is no boundary and you have K, which is of negative codariad dimension, and it's not P2, then there exists a P1 fibration. And the fiber, there's no boundary, so the intersection with the boundary is zero. Naively, you could expect that there should be a fibration proving geometrically that this log canonical divisor is negative, and a perfect situation would be if you have like we had there, if df equals if d times f equals 1, then definitely the codariad dimension of K plus D is negative. Why? Suppose some n times K plus D is effective. Then you multiply it by the fiber and general fiber. And you get that n times minus 2 plus 1 would be non-negative, right? Sen theorem can be understood as a geometric exemplification of the fact that the codariad dimension is negative. A general fiber proves that the codariad dimension has to be negative. You can do it by yourself, not looking at the blackboard. If you have a variety which has, if you have a surface, say, which has a P1 fibration, the codariad dimension has to be negative. Proof is exactly as follows. If you suppose that the codariad dimension, that the canonical divisor after taking some multiple becomes effective, you cut it with general fiber and you get something negative here, non-negative here, a contradiction. Okay? What I want to say here is that naively, you could expect an analog of Sen theorem. That would be that P1 fibration which meets the boundary in at most one point. Indeed, the same argument would follow. If the intersection with the boundary is at most 1, then you get minus 2 plus 1, so it's still negative, and you get a contradiction, right? So that kind of fibration would be a geometric proof, geometric explanation why the codaira is negative. But the life is not so simple. So you can't expect that vibration exists in general. But now you can pose a question. But let me start with the definition. So let me define the height. So X is as before, log del Pezzo surface of rank 1. The height of a del Pezzo surface is a minimal number H such that there exists a P1 vibration of the minimal resolution. Note that I'm using the minimal resolution, not the surface itself, with F times D equal to A, where as before, let me remind the notation, X bar X bar X. This is a minimal resolution, and D is the exceptional divisor. So it's a reduced curve, so the intersection with the general, and F is a general fiber. So it's a natural number. The intersection is a natural number, and the best vibration is when the number is the smallest. Okay. So now I should say that there are many parameters studied for the Pezzo surfaces, for instance, the index. If my surface is Q factorial, then the canonical divisor is Q Cartier. So there exists a minimal number M such that M times K bar becomes Cartier. This number is called the index. Unfortunately, this parameter is unbounded. Of course, you can try to classify Del Pezzo surfaces where this parameter is small, and this has been done for index 2, 3, maybe partially 4. But that's one of the main questions where you can find a parameter which is bounded. And what I want to say today is that this is exactly this parameter. So the theorem, now I will assume here, okay, let me put the theorem with a star. It's not published yet, but you should see it in a month on archive. So if let X bar be a Del Pezzo surface of Picard rank 1, then the height of X bar is at most 4, with a small exception, unless the characteristic of the base field is 2, and then the height of X bar is equal to 6. Now, why is this of interest?
Equal to 6 or less or equal to 6?
It's, I think, equal to 6. But to be safe, there are hundreds of these surfaces, so to be completely sure that you have not missed any of them, it requires some work. But of course, I don't want to go into details of the classification. I just want to tell you how that this, once you have this theorem, the classification is open. It's not that difficult to do. So why? First of all, so we already discussed that, but let me write it again. So if you have a P1 vibration over a curve of a surface which is smooth, and F, say F is a degenerate fiber, then F is a blow-up of this model. There's a zero curve and this is actually easy with the MMP, for instance. You have a vibration. You proceed with MMP, you know that at the end you'll get a P1 bundle. And the P1 bundle is smooth fibers. In particular, a nice thing is that, note in particular, that F is a simple normal crossing divisor. Because if you blow up a smooth curve, you get -1, -1, you have a simple normal crossing divisor and you proceed by induction. You blow up a point which is a normal crossing point. Okay. So I want to say that these fibers are understood rather completely. On the other hand, so what kind of claim do I want to make? I want to say that technology we already have, and this technology is actually rather elementary, to be honest. This part of this story is that classification, in case the height is small, let's say 3 at most, is doable. You just need to be patient. How do you do that? For instance, in case the height of X bar is 1, what does it mean? It means that you take a resolution of your surface. You have this P1 fibration, and you have one section, and other components of the boundary are somehow contained in fibers. But these fibers cannot be too big because you have this condition that minus K bar is ample. You intersect this divisor with components of these fibers, and it turns out that you get many bounds here. But I don't want to go into details. You can imagine that if I have such a strong information about the behavior of D with respect to a general fiber, it needs to fit into degenerate fibers, and this type of work has been done in many instances, in many geometric instances. Okay, it's actually important not only that this bound exists, but it's actually small. With bound like 27, things would be much more complicated. Okay, so I'm thinking whether I should discuss some steps of the. How much time do I have now?
6 minutes.
That's okay. So I'm skipping that part because I want to tell you something about the proof, and you will see how this MMP works here. So before I proceed, I should maybe note that so we have this Pezzo, and we have this resolution. X D is the exceptional divisor. X bar here. Now, if I try to run, I said that the general philosophy is that if you want to understand some log surface, you can run the MMP. But actually, things trivialize here. Because if I do run the MMP on this log surface, then I go back to this surface. The whole exceptional divisor, and I do not learn much. It's an interesting tension between XD, the size of X in terms of the rank, where it's bounded, the number of components in the exceptional locus, how many singularities do I have, how complicated they are, and the singularities of X bar. So there's some tension here, and unfortunately, MMP with this setup does not help much. But once you know what you want to prove, you do the following. So we already know that the codarial dimension of K plus D equals minus infinity. But let me pick any number between 0 and 1. If I compute that, then it's clearly less or equal than the codarial dimension of K plus D, and this is negative. Fine. This means that I could actually play with these coefficients to run other types of MMP. And still I will be on the negative side, which is interesting in the sense that I will get this log modifier space structure. So now, and here's where you use the fact that you want to prove this inequality, this bound by 4. You pick R equal half. You'll see in a minute why is it why it's a good choice. So we want to prove the existence of some vibration, of some nice vibration, P1 vibration on X. Now you see this height behaves in a nice way when you make surfaces smaller. Clearly, if I have X and some birational contraction on Y, and here I can prove that there exists a P1 vibration onto a curve, then I have a pullback, but the height does not change because only some finite number of fibers are affected. Okay, so then the height of X is at most the height of Y. Okay, good. So now we run the MMP for X and comma D. And I will find some other model, and on that model, there will be a vibration which I will pull back. Now, what I want to say is that half of this job is done for free. Okay, so we have this thing. I'm having some sequence of contractions, and at the end, I have some final model. Let's call it, I don't know, D1. This is MMP, but for this specific boundary. So remember that this is something totally different in a sense of numerics, because now the condition is L squared equal than smaller than 0, and L times K plus, if I keep this is reduced, it's half of the smaller than 0, right? So it's a different situation comparing to the case where D was actually a reduced divisor. Okay, here D is reduced here by definition. We take just the exceptional locus of the resolution. Fine, and so I know that the Kodaira dimension of Y plus half of the boundary is the same as the Kodaira dimension of X plus half of the boundary, and this was already known to be negative. So the theorems of MMP tell me that there exists, I know that there exists a log modifier space structure on this log surface. Sorry. Y half of dy is a log Mori fiber space. Let's just read the condition. So, as you remember, there are two cases. I will only discuss one. I need 5 minutes, okay? Case, the dimension of the base is 1. So what do you have? Y, a vibration F onto a curve B, and what? And rank is not that important for me. I just need this condition, which was the intersection with log canonical divisor. If F is a general fiber, then I have this condition for the log Mori fiber space, which says that F times K plus half of D is negative, okay? That was the defining condition for a log modifiable space. But we already know that F, a general fiber, is a zero curve. So let me once again recall that F square is 0, F times K is -2. And now what? Now you know that -2 plus half of FD is smaller than 0. So FD is at most 3. So the height of Y is at most 3. So the height of X, which is by definition the height of X bar, is at most 3. Okay? Corollary. If you want to classify Del Pezzo surfaces, of rank 1, you can reduce this problem modulo the classification in the easy case. You can reduce this problem to classification of pairs y half of dy, which are in the second case. But the second case was that the base is a point, so it's a log del Pezzo surface. This time you cannot expect dy to be 0. So these are log del Pezzos of rank 1. Usually dy is not anymore 0, but here's something very important. As you have seen, one of the theorems of the MMP says that the singularities measured in terms of coefficients improve. And it's easy to see that if you have a smooth surface and a half integral boundary, this is in particular half log canonical. So these coefficients are at most half. And this property is kept unchanged within this process. So this is important. Singularities are actually half log terminal, which here means that all these coefficients of all these coefficients are smaller or equal than half. And in fact, it's not very difficult to completely characterize such singularities by, that's the last thing I'll draw a picture, by showing their minimal resolution, the exceptional loci. And these are canonical. So you have a chain of -2 curves, or maybe a fork. Or maybe a fork of -2 curves, canonical singularities. Or you have A, K star. These are pseudo-canonical, with the resolution divisor being -3 and some bunch of -2 curves. Usually it's denoted by 3, 2, 2. So these singularities are very simple comparing to general log terminal singularities. And the point is that it's much easier to manage log del Pezzo surfaces only with such singularities. Let me just note that the index of the singularity AK is the determinant of the intersection matrix here. If this is say k minus 1, where k is the length of the chain, then this is actually 2k plus 1. So the index of the singularities is still unbounded. We did not reduce the problem to the case of bounded index, but anyway, this is a huge reduction, which like puts 95% of problems with classification to the case of fibration, and the essential difficulties are in height 4. And there is, because I said that the height will be 4. So, and this is where actually it happens. We need to classify the Pezzos of this type. I want to say that you cannot improve this inequality because even canonical del Pezzos, there do exist canonical del Pezzos which have height 4. So it's an optimal bound. That's it. Thank you very much.
Nice, like over time, 10 minutes and 5. Okay, any questions?
So you have the special case for characteristic 2, which is I suppose due to the fact that then you don't have positivity of intersection somehow, or it's not
Here with this approach. So actually, okay, to do this classification, I repeat this procedure to looking for some simplifying morphism. Actually, MMP gave me for free a surface of this type. Now, maybe I'll discuss this in a minute next time. I'm trying to get rid of all singularities other than canonical ones. What I do is I play a so-called two-ray game on this surface, getting rid of all singularities which are not canonical. But when I get rid of them, I get more boundary. Finally, what I propose actually is a morphism onto a canonical log surface. And then I need to recall what is the classification. And here's the difference. It's actually very funny because so far I almost do not use the fact that characterization is 0, non-zero, whatever. So I do use it at the point where I get a morphism onto a canonical log del Pezzo surface, and it's there where the classification differs for characteristic 2. For instance, there exists a canonical del Pezzo of height 4, which contains some very specific curve in this mood locus, and its geometry plays a role here. It's why the height in characteristic 2.
In characteristic 2, what would you do with this 1/2? 1/2.
Nothing, because this 1/2 just lives in Q. This is unrelated. This is a coefficient of the boundary. The boundary has rational coefficients. It's unrelated with the characteristic of the field. It plays no role. The role is the problems with singularities are, for instance, if you have height equal, small or equal than 3, then there's some discussion of the geometry of horizontal components. Then you study the branch points. And if the characteristic is low, then there might appear some additional super geometries like you have everywhere, I don't know, branching points and so on. So you need to be careful here, but this is completely doable. So the other point where you need to go to study very characteristic specific details is when you want to classify canonical del Pezzos in positive characteristic, and in fact this classification is not that old, I think. On characteristic 2, there are some recent papers even this issue.
Yeah, if you so am I right to say if you instead of did x 1/2 d, if you did x 1/3 d, then you get better singularities possibly, but then you get a worse bound.
Exactly
there.
that's the point. You see, if you put 3 here, then the bound you get here is 5.
Yeah.
But it's already non-optimal. It's known that like you get something which is also very hard to study. As you can imagine, I can do height 1, height 2, height 3 with some difficulties, but then you need height 5. And, you know, yeah, so that's a good point. The choice is actually, first you need to observe what, and that was actually very surprising. I did that by looking at papers by Miyanishi and Zhang, trying to make some approach to the classification. That approach did not work, but looking at their pictures, I just noticed that each time I can find some very surprising vibration. And that was very striking, because in principle, you do not expect any bound like that. Singularities unbounded, indexes unbounded, singularities up to deformation, and so on. Most of the parameters you come up with naturally are unbounded. So that was very surprising. But actually, I should say that, so there was another motivation which was related to affine geometry. So when people learned that there is no easy analog of Sen theorem, there was a question. So I have a smooth projective surface of codaric dimension negative has a P1 vibration, generically, except P2. What about smooth affine surface of negative logarithmic codaric dimension? Does it have an A1 vibration? Yes, it does. But if the surface is not affine, just quasi-projective, smooth, then it's not true anymore. But there are some theorems bounding the height of such surfaces under some additional conditions. These conditions were not met here, but in general, the philosophy to study P1 vibrations and how do they intersect the boundary was actually crucial as a motivation here. Okay. I'm actually very curious whether any type of analog of such a thing for Fano threefolds, whether you have some, whether you can come up with some bounded natural invariant like that. Of course, it's a very vague question because you don't expect P1 vibrations for smooth Fanos. But still, it's something very surprising here, and something maybe something deeper than I can see so far.
If you run MMP for generalized pairs,
What?
generalized pairs,
Generalized pairs.
Yes. do you think that you can obtain something interesting in your direction?
Yeah. Yes, you can. Like the MMP works for instance, good classes, generalized minimal resolution, class defined by Fujino, that you don't need to assume that X is Q factorial, but if you do have a Q factorialization so that the coefficients look like for canonical are smaller or equal than 1, then in this class MMP works. I mean, you need MMP to work in some class. Yeah, sure, most likely you can work with general spice, but like, what would be the question? Because here, my initial situation is actually extremely simple because I take a minimal resolution. I'm in the log smooth case, right? I want to understand X, but I'm getting rid of all the resolutions. So actually XD is log smooth. So no.
So yeah, no problem. You want, for example, the main problem is to classify the Pezzo surface, right?
Yeah, the minimal
And
models.
you use the MMP to use these techniques and have some.
Yes, I use MMP to produce some very specific morphisms on models which behave very nicely. Yes, that's true.
Yeah. But I know, for example, people use the MMP for generalized pairs.
Yes.
To get something more interesting.
Like what?
Like, for example, Barker vibration. So the effectivity of a Barker vibration using the language of generalized pairs.
Okay, yeah, might be.
There's no real generalization in this case. It's the same.
Is the same?
No, but I think he says that you might also discuss the divisors D, which are what, for instance, not necessarily effective.
Not necessarily effective.
Yeah, I think so. That would be this kind of generalization in this case. But to be honest, I don't know. That's a question of purpose. What would you like to do with that? I understand that you can get some specific vibrations. That's true. Hard to say.
Yeah, I see.
Anyway, our speaker will be here the next couple of days, at least for tomorrow. We're gonna restart this afternoon at 1:30. And the meeting for tomorrow will continue tomorrow afternoon.
Okay.
Have a good lunch break.
Is there a website for the workshop? Like,
Yeah. And you can just
Go to Serget,
the website.
Serget, then go to events. Events, and then Serget, then go to events. And then the second one. Direction.
It's nice to give a chance to prepare my slides for my class tomorrow. But
Yeah, exactly.
workshop talk. for calculus tomorrow. When is the talk? You're missing all the postdoc seminars. When are the postdoc seminars? I mean, I didn't get any. Thursday. One.
Yeah, je te présente de Macduff. So here was
Even for you, it's not. No? I told them you're able to make. I'm reading you, but just basically you and the organizers.
What do you?
Organizers now, actually.
Yeah.
Yeah, they go on big. If I don't have to do anything.